Welcome to Project 21020, Drop Volume Algorithm and Analysis System, sponsored by Roche Tissue Diagnostics. Our digital poster predominantly showcases our overall process of the system. For this presentation, we will walk you through the problem presented to us from our sponsor and the agile process that allowed us to deliver a viable product. The drop volume system provides Roche with higher accuracy for patient diagnosis. Currently, Roche uses the Benchmark Ultra, a staining system to detect patient diagnosis. To deliver the most precise and accurate diagnosis, the system needs to ensure that the proper quantity of reagent is being dispensed on every sample. If the amount of reagent is insufficient, our system could provide a volume output to Roche technicians for validation. This brings awareness of the system imbalances and errors prior to delivering diagnosis. Our sponsor set forth requirements to ensure the system algorithm provides better accuracy and precision. Our system then outputs its calculation to a storage device for lab technicians to access the data. Key functional requirements revolve around performance measures such as an accuracy of 20 microliters and a precision of 5 microliters on a 95% confidence interval. Our drop volume detection system is capable of identifying the volume of falling reagents to the required degree of accuracy and precision. In order to fully understand the drop detection system, let's walk through the steps of the drop detection process. First, a signal is received from the Roche system, indicating that a drop has occurred. The light curtain sensor then collects the analog data of the falling reagent and sends this to the drop detection system. The system block diagram breaks down the complex system into an easy-to-understand architecture, with system boundaries for a better understanding of our system. We have 3 primary sections. First is composed of the analog signal or light curtain sensor received from the Roche system. The next section is the Raspberry Pi, which converts the algorithm to a volume estimation. And finally, we have the logger that stores the data through the Raspberry Pi and onto the microSD. This provides Roche with a compatible solution to improve accuracy and precision of their current system. The agile process allowed for readjustments as our project met feasibility early on, allowing for hardware implementation through the change request process. We were able to add value to the customer by reassessing our MVP into 3 stages to meet our sponsor's critical needs. The 3 phases were preliminary design review, which focused on a minimum viable product, critical design review for hardware implementation, and the last iteration for the final verification process. Each phase was tracked through the use of smart sheets, where we assigned tasks per team member into 14 sprints. This allowed clear communication between the team and our mentor.
Our initial design process began with analyzing light sensor data from over 300,000 drops of water and building an algorithm to predict the volume based on this data. This was our first minimum viable product, which also proved feasibility. Different pre-processing methods and machine learning models were trained using 80% of our data and tested on the other 20%. We also developed a testing framework to quickly assess the accuracy and precision of these different models on a 95% confidence interval to provide final verification of the algorithm. Our best performing model, based on the tested accuracy and precision, met and exceeded our system requirements on the stored light sensor data by using a recurrent neural network with custom pre-processing, which served to distill plots of 20,000 data points down to 128, allowing for faster computations and reduced storage size. After proving the algorithm to be feasible through our first deliverable at ISR1, we proceeded to the hardware design phase to integrate our algorithm with Roche's Benchmark Ultra through our system, which will plug into and work with Roche's current system. After various trade studies, we decided to use a Raspberry Pi as a processing unit for our system, as it is cost-effective, provides sufficient processing power, and it drastically lowers development time. Our completed hardware design, with trade studies, a system block diagram, and circuit simulations, is what we presented at ISR2. We then began developing the final system, which integrates the software and hardware portions. This system first uses the tissue dye dispenser as a trigger to start collecting data. Then, the Raspberry Pi begins reading analog input data from the light sensor using a data acquisition hat. The Pi then pre-processes the input and uses the pre-trained algorithm to produce a volume measurement. This volume measurement is then output back to the benchmark Ultra using pulse width modulation. Additionally, all of the raw and processed data is logged along with the predicted volumes on the Pi to be used by technicians in debugging and in further development. Our final technical data package contains 8 sub-documents with their most current revisions. The indentured document list keeps track of all documents while easily navigating you through each section of our system. For verification, our system went through 2 main phases. For feasibility, we tested the algorithm accuracy and precision by comparing the algorithm's volume calculation with the true volume provided by Roche for the entire test set. In this case, Roche measured the true volume by weighing each drop and dividing by the drop density. The algorithm's prediction was within plus or minus 20 microliters of the true drop volume for 97.7% of the test set, passing as the requirement was for 95% of the test set. And the algorithm had a precision of 4.3 microliters, passing the requirement of 5 microliters. Due to COVID-19, we were not able to test on Roche's actual tissue staining system, but by constructing an apparatus with a tissue dye dropper and a light sensor, we were able to simulate the parts of the system relevant to our testing. Using this, we verified our accuracy and precision by comparing a set of drops in each of 5 different volume groups: very low volume, somewhat low, the expected volume, somewhat high, and very high volumes. Additionally, we verified the input and output constraints, as well as the logging and storage requirements using this setup. The input and output was verified in the lab using an oscilloscope connected to the GPIO board. The output time was verified in code using the Python time libraries.
Verification for the accuracy and precision requirements using the hardware implementation has not yet met the passing threshold. This is due to differences between the light sensor data from the training data and the verification data. We currently have 2 concurrent paths on the root cause, and we continue to work to resolve the issue in order to deliver a fully packaged, functional product. From the Agile process, we learned to keep our goals aligned and plan for changes through an iterative process, starting with a scheduled game plan to allocate proper time and develop an MVP to determine the best focus for our project. We learned that taking the time to evaluate potential risk is necessary to ensure the delivery and quality of the final product meets the standards of our sponsor. Lastly, we learned how to adapt to changes and work remotely during a pandemic. As agreed upon, all final deliverables will be electronically delivered to Roche Tissue Diagnostics by May 6th. This includes a final technical data package, the hardware package, a user manual, and all software through the GitHub repository. The hardware will be delivered in person, which includes the GPIO plate, signal amplifier, light curtain sensor, and the Raspberry Pi 4 with the DAC hat. In essence, our system has provided Roche Tissue Diagnostics with higher confidence in diagnosis by ensuring each tissue sample has the proper amount of reagent needed in determining a verdict to their patients. Our system verification matrix shows all completed deliverables and test methods, along with verification test sheets. On behalf of Team 2020, we'd like to say thank you for attending our virtual presentation.